Hello, everyone. I'm Susan Nash, AAPG, and we have a wonderful program today. We have Jon Rotzien and Andy Pepper, and the topic is Deepwater Reservoir Architectures. And it's something that is enhanced by extensive field experience by Jon. Jon just came back from several different field trips, one in France. And it really makes a big difference to be able to see the actual rocks versus just the log signatures or core samples. So some of his findings today have a lot to do with what the integration of experience plus the subsurface and petrophysical data. And I also wanted to mention too that this is part of a series, the AAPG Academy. And in this case, we're hoping that people who are involved in actively exploring, developing reservoirs will really find this beneficial. We are recording it, and this will be part of an ongoing series, as mentioned, but also it leads up to some of our other events that we have, such as Image that you might have attended, and also our regional events. So before I'd like to say that Jon Rotzien is here presenting, as well as Andy Pepper, and then we will have another Deepwater themed presentation on December 8th with Victor Ramirez. So anyway, I'd like to go ahead and let you're sharing your screen. So I'll just encourage you to go forward.
Thank you so much, Dr. Nash, and thank you all for being here today. It's really a privilege, and it's been a ton of fun to put together this presentation and to get to work with Andy on it. So I hope you all learn a lot, take away some new knowledge, and I very much look forward to some of the questions you may have based on the information shared here today. So thanks again. One of my favorite topics, Deepwater Reservoir Architecture. And this image right here is of the Ventura Avenue anticline, part of a 1 billion barrel field in Southern California. One of the first places they actually mined oil and gas from turbidite reservoirs. So some of the earliest deepwater production from turbidites anywhere in the world. And you don't see a lot of scours or deep erosional surfaces in many of these rocks. And so likely they're laterally extensive lobe deposits. But this is one of the questions we ask ourselves when we drill similar successions and wonder, will these reservoirs end, and how do we know? So that's some of the questions motivating today's talk. There are a number of challenges with understanding deepwater reservoir architecture, and we're always asking the question, what happens when our production profiles don't match expectations? And there are two big challenges: understanding the reservoir architecture, which comes down to a basic understanding of the rock, the major surfaces, the fluids, and the mixing and the overturning, the quality of the reservoir units, the connectivity and the sheet sand theory, all good reservoirs must eventually come to an end, so there's no such thing as a sheet sand. We'll look at heterogeneity at various scales, from the pore scale all the way up to the basin scale. And then you need to understand the 3D context within the sedimentary system. And the second big challenge is predicting the reservoir architecture, and it comes down to an interpretation of the data and really trying to be disciplined with resisting the modern dogma of the day and coming up with new interpretations based on the data. And it also comes down to an application of the current understanding of what we think we know about how reservoirs are formed and how they produce. And then finally, it comes down to execution of this modeling expertise. These are some of the topics covered in our Image short course sponsored by AAPG earlier this year in Houston with many of our colleagues. So to get at this question of deepwater reservoir architecture, there are several themes we must explore. One of those is deepwater sedimentary processes, classic deepwater deposits, deepwater lithofacies, architectural elements, also examining reservoir architecture at multiple scales. And then I'll summarize and present some ideas on how to learn more if this is a subject of interest to you, or if you think you'll work deepwater reservoirs, or if you're thinking about working deepwater reservoirs, or if you currently work them right now. So it's for everybody. And it's good to see a lot of familiar faces, and look forward to meeting you all in the future if I don't know you already. First off, got to say thanks to the Dream Team for creating the seminal treatise on deepwater. It took about 11 months to do, and this was our little celebration at Image. This is about a third of the authors. And these are some of the finest geoscientists and engineers and economists in the world. And so this wouldn't have been possible without them, and really need to give a big thanks. To get at this question of deepwater reservoir architecture, it helps to understand some of the basic processes that go into forming them. Many of them are controlled by downslope processes, sediment gravity flows, and a subset of those, turbidity currents. They're driven downslope by gravity acting on the particles in the flow. And naturally, these distribute sediment in predictable patterns on the seafloor. These are subdivided into debris flows, high density turbidity flows, low density and ultra low density turbidity flows, as shown here in this model, this cartoon. And they're subdivided into nose, head, body, and tail parts. And those deposit different types of first order architectural elements. These are coarse grained to fine grained, depending on the sediment available to the system. And this image at the bottom is basically reflected in the basin. So the coarsest grained deposits, the R1, R2, R3 deposits, which we'll look at later in this talk, are deposited in more proximal zones. And the TC, TD, TE deposits, in theory, are generally deposited in higher abundance in more distal parts of the basin. What makes deep water different from other types of depositional systems are the processes and deposits. So these are some of the classic reservoir faces you'll find that many oil companies produce from. Some of those are formed by, as shown in A, suspension deposits, catastrophic collapse of a fully turbulent flow that suppresses bed load traction transport. Sometimes you can find subtle dish structures, pillar structures in these water lutriation fabrics. These can be very high quality reservoirs. B shows evidence of traction structures formed beneath a near bed laminar sublayer. These form plain beds, ripple cross laminated intervals, and those can be actually higher porosity and permeability just due to the sorting processes that occur during this depositional process. C shows an inversely graded traction carpet. One of the few times you'll see inverse grading in deep water deposits. This is formed by shear of an overlying high density flow that rework some of these gravels of the bed, a very powerful bypass fabric. And then D shows what happens when you introduce a lot of resistance to flow or cohesion or matrix strength into the sediment gravity flow. And oftentimes that'll change something that may be quite turbulent into something that flows in a laminar debris flow fashion. And this creates debrites, where none of these coarse grained particles are touching. They're sort of floating in this muddy matrix. Oftentimes these are non-reservoir, unless you frack them, like what they're doing in West Texas in the Permian Basin. Nowadays, it's a little bit more complex. This is one of my favorite cartoons by Francisco Javier Hernandez Molina, showing the range and variability of marine and deep marine processes. And as you can tell, marine settings are quite complex. There are many different inputs and processes, and mixing of these processes, which is an area of current research around the world by some of the top tier academicians and people working internally at oil and gas companies, is what happens when you mix some of these processes to create really high quality reservoirs that we haven't even fathomed yet. This is what some companies are exploring for today, which is really exciting to be involved in deep water just for that aspect. So to be a successful explorer, appraiser, and developer, if the evidence presents itself, you need to be able to change your mind. And I hope to present to you a lot of evidence today that will help encourage some of your exploratory workflows. But here we've got evidence of turbidity currents, slides, slumps, creeps, evidence of the climatic impacts on deep water from polar margins to the low latitudes, and what happens when you transition from the shelf to slope to basin floor and move out into the hemipelagic and pelagic realm. And deep water is really one of the true frontiers that we expect to learn more about over the next 10, 20, 100 years on Earth. One of the main ways to map and interpret deep water reservoirs, and wherever you go, any deep water basin on Earth, there's a range in variability in type of the mappable lithofacies you'll find, rock units that you can use to better understand deep water reservoir architecture. And it varies from basin to basin, but there's a good set of 10 that you may find in a deep water basin if you're provided all the different grain sizes. These result from many different marine processes. They are central and critical to petroleum systems analysis. These are very architecturally diverse, and these are quite useful in mapping and interpreting them at various scales. So some of the major lithofacies you'll have in deep marine areas are mudstone, matrix supported conglomerate, clad supported conglomerate, and then it gets thinner and thinner in terms of the bed thickness, which is a really valuable way to be able to map and interpret them if you're looking at core or image logs or any data where you can subdivide the bed thicknesses. That's based on some of the earlier work from Campbell, who gave us a great amount of information on how to analyze core during his career. You get things like thick bedded sandstone, very thick bedded sandstone, medium bedded sandstone, mudstone, thin bedded sandstone, mudstone. And then these really interesting deposits, chaotic deposits, which can include slumps and injectites and MTDs and all sorts of really funky fabrics, which is described in great detail by Tiago Alves, Sebastian Cardona, and Marilyn Rodriguez in our new book. Another really important principle in understanding deepwater reservoir architecture is looking at architectural elements. And whereas sequence stratigraphy generally divides things top down in classic Texanian form from sequence boundary to sequence boundary, or if you're a Texan like me, you go between maximum flooding surface and maximum flooding surface. But if you want to build things up, as in bricks going into a building, what are the basic building blocks of a deepwater reservoir? You need to use architectural element analysis. And it's based on some of the great work from Lowe and Ghosh and Lowe in the 90s and early 2000s. And it's gotten a little bit more sophisticated from those years. And this differs from other proposed classification schemes of reservoir architecture. Some of the great work from Mile, working fluvial systems, or other great deepwater practitioners, in that it uses lithosomes and can be applied in 1, 2, and 3 dimensions, because in many deepwater successions, especially many of the reservoirs we produce from, they're really fine-grained. And it's really difficult to notice where some of these key stratigraphic surfaces are to place them in a sequence stratigraphic framework. And so you need to use the lithofacies to build higher and higher orders of architecture. And this is very favorable for characterizing and interpreting deepwater reservoir architecture, especially in these fine-grained systems. So the basic building blocks of the beds are the sedimentation units themselves. And those can be subdivided into first-order architectural elements, let's say a Bauma division, a Bauma TC or a Bauma TA, or any of the other types of bed facies schemes. And once you pile on a lot of similar bed types, that'll form a lithofacies with very similar porosity and permeability, same bed thickness. Based on the slide we just looked at, you can create higher and higher orders of architecture, and ones that even resemble genetic elements, such as the fill of a channel or a channel levee complex, which would be 4th and 5th order architectural elements. And this can be applied in 1, 2, and 3 dimensions. Doesn't matter whether you're working with core, 2D seismic, or 3D seismic. Anyone can use this in their basin. So let's drop back down to those first order architectural elements. This is some examples of downslope and along slope flows and what they produce in terms of the first order architectural elements. And it's arranged in a rubric, if you will, with turbidity currents in one column, column 1, column 2, debris flow deposits, column 3, transitional flows, and column 4, multi-process flows. And these are generally considered first order architectural elements. So we've got suspension deposits for turbidity currents, traction deposits in B. C shows a traction carpet, and then the very low density turbidity current deposits in D. For debris flows, we've got matrix supported and class supported debrites, mud class rich linked debrites, and then also mud class rich zones that occur at the base of the bed. For transitional flows, there are a number of different models: slurry flow deposits, argillaceous sandstone. This is what happens when you merge fluid turbulence and matrix strength, creating something that could be a decent reservoir or maybe not so much, just depending on the amount of disaggregated clay you have in these types of deposits. And then multi-process flows, including ones that have been made famous by people like Palmyra, wave-dominated turbidites in the Minturn Formation and in parts of Antarctica, tide modified turbidites, hyperpycnites, and then some of these contour reworked sands or bottom current reworked sands, which is a very interesting part of our research today. And the distribution of these rock types in part determines the 3D reservoir architecture. And the fourth point I'd like to make is that the range and variability in the porosity and permeability determine the quality of the reservoir. So chances are, if you've got a highly variable reservoir, you'll see many of these different traits in your reservoir. So now let's move up a scale to the second order architectural elements. The basic building block of deepwater reservoirs is the bed or sedimentation unit, which is a bit of a mouthful, so bed simpler. Most of these deepwater sedimentation units fine upward and contain both the reservoir and non-reservoir facies, including the seal. And the sedimentary process, grain size distribution, and overall sedimentary environment control the resulting reservoir distribution architecture. These are examples of coarse-grained high-density turbidity current deposits shown in A, tend to be quite gravelly along active margins. There are some very famous outcrop examples from Chile and California, parts of Malaysia. B shows the classic low-density turbidity current deposit made famous by Bauma decades ago. And the one on the base shows very low-density turbidity current deposits proposed by Shamagam back in 1980. A famous geologist, Don Miller, said Deepwater is home to the graded bed. Most of these are graded, but chances are they will depart from these simplistic models in your basin of interest. That's the caveat. Now, if you want to go to where it started, it's basically like taking a pilgrimage to the foundations of turbidite reservoir architecture and where it all began, if you will. So this is along D21 road, the ore category Tour de France climb, Col de Torini. And at this climb, this bend right here shown in red, this is where you'll find the original Bauma sequence, which Bauma sampled for his thesis. And if you looked at it, if you know the Bauma sequence that we teach, undergrads at University of Houston and UT Austin and other universities today, they would say, well, that really doesn't look like a Bauma sequence, does it? And we'd say, that's exactly right. You're a really good student. You're going to get an A. And so when you take a look at some of these deposits, they've got some very sharp grain size breaks, and they don't really show the true suite of structures that Bauma envisioned. Further, it's a little bit difficult because if you see in figure 14, the base of the bed isn't included. So still, it's a bit difficult to recognize what is the original Bauma sequence, and there is some uncertainty in that. When looking at core today, I'm a person who likes to have it all out in front of me. This is a useful rubric that you can use to examine your deepwater reservoirs and reservoir architecture from those basic building blocks. And it follows that same sort of rubric design that we looked at those first order architectural elements in previous slides. That shows turbidity currents on the left, the coarse grained, fine grained, and the very fine grained models. The ones that involve matrix strength and fluid turbulence, the hybrid event bed, the argillaceous sandstone bed, and then the slurry flow deposits. And there's a caveat with that one. You really need to read the paper by Lowe and Guy 2000 to understand it in detail. The third column are contour current and rework. Some of the models by De Castro and De Weger, and the original by Gonthier and Fougere. And then some of these shallow marine modified either by tides or river fed or wave dominated. But what about some of the larger scales? Javier Hernandez Molina once said, we used to have such poor resolution with the seismic data in the 90s, used to think the seafloor and subsea was so smooth. Now we see all this detail. And this is using coherence data. Many of us take it for granted, but it was invented by Marfort in his lab back at Amoco in the 1980s. And we can see all sorts of really interesting details in the subsea. These data are from New Zealand, showing a variety of sinuous channel patterns, subsurface volcano, and a number of faults. So now let's zoom out to look at some of these different types of models envisaged from working data like this. But our knowledge of deepwater depositional systems wasn't always so advanced. Back in the 1960s, there were very simplistic patterns about where different types of the Bauma sequence would be found in an unconfined setting. In B and C, we start to look at some of the stacking patterns that we'd expect from these traditional lollipop fans and then belly-fed deepwater depositional systems by that model by Stowe and Piper in 1984. Fast forward to some of the excellent work by Redding and Richards, 1994. This shows what happens to distributary patterns when you're fed by a canyon. And then moving into late 90s and early 2000s, some of the example work by Bobuff and Mail, some of these excellent geologists, looks at what happens to these submarine fans when you introduce some of the climatic impacts. Let's say, what if it was sourced from an aeolian setting and then sent to deep water with a lack of clay, and almost everything is very fine grained. That's what we can learn from some of the brushy canyon formation outcrops. And then Mile, some of his excellent work from offshore West Africa and conjugate margins shows what happens to sediment distributary patterns in the reservoir architecture when you start to introduce mobile substrates, mud and salt and things like that. And you can trap a lot of the sandy reservoirs on the slope, in this case, preventing it to getting from the deep to the deepwater basin floor. But these models have always been built for exploration purposes, and it took a certain amount of faith to advance these, work in the data that these folks worked. And so you tend to wonder, like, what if I'm wrong? What if somebody makes fun of me for creating a new model? But I think all these explorers thought, well, what if I'm right and I stand to make the next big discovery? So I think we're going to start to see new models over the next 10, 20, 30 years that really we never envisaged right now. So it's really exciting time to be part of this exploratory effort. Let's talk about some of the major deepwater depositional environments that have a key control on reservoir architecture for the last several minutes of the talk. Then I'm going to hand it off to Andy. So canyons, these are basically the rulers of the system. They are capacitors of sediment. They transport sediment and collect it. And they're very large scale. These have highly variable processes. They can even include shallow marine if the canyon head incisors all the way up to the shelf and potentially the beach like the Monterey Canyon does. And this can show a wide variety of different types of deposits that we've previously discussed. MTDs, slumps, slides, matrix and class supported conglomerate, and evidence of very sandy deposits that may represent a deep water braided system versus the interbedded sandstone and mudstone that may represent a levee channel system. This is also one of the type sections for understanding sequence stratigraphy along active margins. This is the Venado sandstone of California. Channels, these are typically downslope of canyons, and those also collect and receive and transport sediment downslope. When they're very active and alive, they send sediment downslope, but once they get filled, they expire. But they're preserved for us in the rock record to examine, like this one at Pukearwe Beach, or the Taranaki Basin Miocene deposits just northeast of New Plymouth, New Zealand, on the North Island. And this shows some of the really interesting depositional architecture you find along channel margins. And it also shows a repeated pattern that we often find along channel margins, which illustrates one of the key points in terms of channelized connectivity in these slope to base of slope systems. Here you see a thick interval of mudstone at the base of this channel, and that can partition some of these channelized reservoirs, which is a key geologic risk in understanding these. And then if you drill or move along upwards in the channel fill, it gets sandier and sandier before you get to the thick to very thick bedded sandstone. But all those onlap and pinch and end at the channel margin through here. But you can see it's a very complex channel margin too. They're very simply drawn in many diagrams and cartoons, but when you look at them in 2D outcrops, you can find a lot more interesting detail that may help you explain why you're not getting the production profile you first expected. Levees, naturally bound channels, typically they're quite silt and clay rich. If they weren't, they wouldn't really stay in place. There are very few examples of very sandy levees because they tend to not have a lot of cohesion, and they'll just get busted through by the next really erosional or powerful turbidity current. These are subdivided into internal and external levees. This is based on some of the great work from Emma Morris that their team did in South Africa in the Pardrikal section. It's subdivided by levee crest, and you can get almost any different type of sedimentation in levees. You can get overbank and crevasse splays, you can get sediment waves, you can get MTDs, debrites, slumps, slides, as well as a whole bunch of turbidity currents. And some of these can even be modified if you've got a persistent along slope current moving at 20, 30 centimeters a second, although that's pretty quick and can act to rework some of these deposits in levee settings. So oftentimes these are underrepresented in terms of their complexity, but these are very complex and much more work needs to be done in these. We're really just at the tip of the iceberg with understanding levee anatomy and geometry and how they evolve and how they look different in asymmetric sinuous channel systems, as well as straighter channel systems, and how they look from outer bend to inner bend. And there's a lot of variability. Lobes or splays, this is the default type of fourth, fifth order architectural element in deep water systems. Most deep water systems, again, very different from fluvial systems where you've got this sharp interface between the flow and the channel and then the air. Here, you don't really have that huge density contrast between the sediment gravity flow and the ambient seawater. Oftentimes it's fractions of a gram per cubic centimeter. So this stuff can flow out in all these different unconfined forms, and many of those forms are lobate. The term splay or lobe is mostly interchangeable. Some people differentiate it, but this shows some of the cartoons of the various play types that some companies have when looking at splays. You can get channelized splays, overbank splays, crevasse splays, which naturally break through the levee. Often terms are bigger, longer lived, more signs of erosion. Avulsion splays, which can lead to rerouting the entire channel form, and then some of these frontal splays, which can be quite big, but not all flows always make it to the end of the channel and reach it to this area. There are some splays that aren't shown in this diagram, but this is a simplistic cartoon of how these look. So in summary, deepwater reservoir architecture is controlled by sedimentary processes, these key stratigraphic surfaces and non-stratigraphic surfaces in the deposits. And understanding the range and variability in reservoir architecture and these architectural elements is a critical skill that everyone needs in analyzing subsurface fluid flow. Reservoir architecture is controlled by the deepwater sedimentary system at various scales, as we've looked at today. And I'd like to pose the question, are there new processes altogether that explorers will discover that can lead us to really exceptionally high quality reservoirs that are well connected and lack a lot of complex architecture that would prevent efficient fluid flow? And I think we need to keep a quote from Richard Sears in mind. I wouldn't have seen it if I hadn't believed it. I hope some of the things today may have been a little bit new to folks and encourage people to say, hey, if Rosine's seen this in different basins, or if Andy's seen this in different basins, maybe we should look for it in our basin, and maybe we'll have an upside surprise. If you're really keen to learn more about these types of observations and the science behind it, schedule a consultation, join a course. There are many courses around the world. Andy and I teach these routinely. Go to a conference. We've got a great GeoGolf program lined up for you with Charles Sternbach organizing that. APG GTW in Lisbon is finally going to happen, we think, on mixed systems, and I've got a slide on that next. Image 2023 is going to be an absolute blast, and Perkins Rosen will be the 30th anniversary of the Deepwater Conference sponsored by Shell back in the 90s. We're going to bring Deepwater back in a big way next December 6th through 8th in 2023. So I hope everyone can come to Houston for that, one of my favorite cities in the world. Join a research group, subscribe to a journal, also get out into the field, and there are still COVID concerns. So if you're concerned about that, there are some methods to lead safe field trips, and that's described in this GSA Today cover article. So another plug for some of our AAPG conferences around the world. We really think this is going to happen this year. It's been pushed back a few years, but we've still got a whole bunch of enthusiasm for it. You can see some of the cast of characters organizing this, and I've told a lot of my friends about coming to Lisbon for this great conference because I said it'll be a fantastic time to learn about some of these fields, including the big discoveries by E&I, the 90 TCF Coral Mamba discovery. Wow, let's try to find more of those. And so my friend said, well, it's Lisbon, it's very far from Houston. And I said, well, Lisbon's a great city, even though I love Houston too. But I said, Emiliana Moody will be there. And so now people are signing up in great abundance. So I hope everyone can make it for that conference. It's going to be a great time. Thank you.
I'm so glad you mentioned that. And it's really exciting to see how these courses are going, and the course that you had at Image was such a success.
Thank you.
So great. Well, we've got Andy Pepper. Would you like to share your screen? And so it's super exciting. And don't forget to purchase a copy of the book. Here we go. Andy, you're muted. Okay, so Andy is still muted.
Okay, here we go.
There we go. Good.
Are we good? All right, so we're going to start in these few minutes with some comments about pressure, often used to try to prove or disprove continuity of these very layered deep water reservoir systems. I think it's really important to talk about the processes of reservoir filling and mixing before we try to interpret fluid data and fingerprints and so on. And then I'm going to talk about a couple of deep water reservoir connectivity studies that I think follow a kind of a good practice in terms of thinking about the mechanism first before we talk about the fingerprinting and so on. Okay, so the first comment then is really that it's really important to work in overpressure space rather than total pressure space. It really expands the scale and much easier to see subtle changes and offsets in pressure gradients this way. And then the comment I'll show in this example now that really pressure data can only demonstrate disconnectivity. It can't really be used to prove connectivity. And I'm just going to use one of the scenarios from the training class that we teach. And basically it's an overpressure diagram versus depth. We're on the crest of an anticline. We have a sandstone, a mudstone in between, another sandstone, and then a mudstone above this. And the lower section here is hydrostatic. so that the capillary pressure is really the only thing that it's determining the column height within the lower reservoir. And then when we get into the upper reservoir, see, that's a little bit different because we're actually building excess pressure in the seal. So this is a system that's often referred to as in an overpressure regression. Let's fill. So we percolate through the sandstone. We're filling it bottom up. We're percolating through sandstone. We find the capillary pressure boundary. So we build an overpressure head at the top of the column. We're building the column into the sandstone. Now we reach the critical entry pressure of the mudstone, and so we percolate through this mudstone. We don't saturate the mudstone because this is basically just looking for the spanning volume that allows us to reach the low capillary pressure medium on the other side. And now we're filling the shallower reservoir, which at the moment we only see the capillary pressure boundary at the base of this seal now. But remember, I mentioned to you this reservoir here is actually overpressured. And so there's water pressure that's added to the capillary pressure. So the total resisting force now is the sum of those two things. So you're going to see now that the upper oil column can back off that higher resisting force that's the combination of capillary and hydrodynamic forces in the seal there. You'll notice now what's happening is that I'm pushing the column into the mud rock. So we're creating an unconventional reservoir, by the way, and we're doing that both in the top seal and the bottom seal, because basically we haven't reached the column capacity of that upper hydrodynamic seal yet, and so we can just keep building this enormous column. And now we've saturated on a geologic timescale, on a filling timescale, we've saturated the whole system here, including saturation in the mud rock. These again would be an unconventional reservoir, and now we actually have a column that is continuous on this overpressure profile through the petroleum phase here. But the one thing you can point I want to make here is that it's a nice example of where fluid connectivity cannot prove, or pressure connectivity cannot prove fluid connectivity, because this system here evolved over millions of times slower than production. So we're going to pull the fluid out of these reservoirs a million times faster than this system was able to set up. And so it's just a nice example here of how a fluid gradient that looks like everything's connected can be across a medium that has no connectivity on a production timescale. And so these reservoirs are going to deplete completely separately on a production timescale. So you cannot prove connectivity with pressure data, despite the fact people seem to want to do it. Okay, so then the reservoir filling and mixing, I want to talk about how fluid distribution depends on the filling and mixing history of the reservoir. Density-driven overturn is the dominant mixing mechanism during the reservoir filling process, and that the rates of that density overturn depend on the rock and fluid mobility of the reservoir system. So that means then a fluid fingerprint doesn't necessarily mean a compartment, because if it's just poorly mixed because it hasn't had time to overturn and mix up, then basically you have a continuous thing. It basically just doesn't tell you have a bunch of compartments in there. And then perfectly continuous reservoir systems with low mobility could basically have these unmixed signatures, which shouldn't be interpreted as fluid connectivity fingerprints. And I see geochemists making that mistake time and time again. So basically, we need to watch out for gravitationally stable reservoir fluid variations. I'll show you that hopefully in a couple of cartoons I'm going to show now. Okay, so this is kind of like what happens, an attempt to sort of show what happens in the initial filling. I call this sort of sideways filling history. So we've got a source rock down here that's mature on the flanks. It's basically expelling vertically, and so the charge is coming laterally into this reservoir. So basically, what's happening is that the earliest expelled oil accumulates first, and then the lighter oil comes later and later in the filling history. And so that's a gravitationally unstable system. So what happens then is that the light oil that's coming in latest has the ability to overturn and mix up this reservoir. So what we really need to understand is what is the time scale of that mixing, depending on how the mobility of the reservoir, it may well be that overturning process can't happen quickly enough. And what we, as I say, what we don't want to do is to diagnose fingerprints and compartments when in fact it's just a poorly mixed reservoir. So one of the most important charts, this is from William England's work at BP in the late 1980s, it's probably the most important chart in any reservoir fluid fingerprinting or continuity study, is to understand this diagram. The main point on it here is this red curve. And what William did was sort of establish, based on the fluid mobility, so this is the permeability divided by the viscosity, so the mobility of the fluid system. And it's basically telling you how long in millions of years it takes to overturn given this kind of reservoir mobility. So you can see here that depending, when we get to really low permeability, the overturning is tens of millions of years. And when we have extremely permeable or mobile fluid systems, it's thousands of years. So it's a huge thing to try to understand. The Gulf of Mexico, something like the Mars field would overturn 7,000 years. It's got high permeability and good viscosity. Why does what about something like the Noco heavy oil? Well, that's basically got great permeability, but tremendously high viscosity. So the overturning rate in that would be 3 million years. The reservoir has probably been filling for 20 million years. So that's probably in partial state of overturn. And you may have wondered why in these shale days, why do we have low GOR oil up dip of gas? And it's basically because if you look at the mobility of that system, 100 nanodarcies, and even with the gas viscosity in the Barnett, it would take 1 billion years to overturn. And that's why in those unconventional reservoirs, we just basically have the fluid arranged more or less in the order in which it was expelled from the source rock from low GOR up dip and down dip. So this idea of the filling and overturning is really, really, really key. So the other kind of thing that's really, really important is to understand what I'm going to call it mushroom thing. So this is more mushroom filling. So this is more like a typical most Gulf of Mexico reservoirs, I would say, generalizing, behave like this. So the fluid comes in, the bottom one, we reach a leak point, a capillary pressure is balanced by the column, and then we begin to leak to the next one. And it's always the earlier fluid that starts leaking first, and it's backfilled by the lighter fluid. So we tend to get these variations in maturity with the lower maturity fluid at the bottom and at the top, and the higher maturity fluid at the bottom. And obviously we would not interpret this as a connected system because we have light fluid underneath heavy fluid, which is not gravitationally stable. So it's really obvious that this is a layered system with poor vertical connectivity from just the juxtaposition of dense fluid, right? Another one thing to watch out for is if these reservoirs started life in many cases as a biogenic gas reservoir. And so because the filling's coming in from the bottom, the biogenic gas is always at the top. And so as it moves into the solution gas of the oil, you're going to get a different biogenic fingerprint in the solution gas here compared to here. And you wouldn't interpret that as a compartmental difference, compartmentalization difference, because it's gravitationally stable. There's no reason for the overturn there because we've got light fluid sitting on top of heavy fluid and more heavy fluid coming in the bottom. And so until the system gets much more mature and we get a lot more light fluid coming from the kitchen, we're going to have a fluid fingerprint difference in a completely connected reservoir. And similarly, if this was biodegraded at the bottom of the column, that's gravitationally stable as well. And so we would not diagnose biodegraded oil and a fresher oil here as a compartment difference because it's gravitationally stable, and it should stay in that sort of equilibrium grading of composition. And then this kind of style that I've called mushroom filling, which is basically where we start to leak from one reservoir to another, and we sort of and as more and more fluid comes in, we can end up with a graded column in here, which basically means that it's always the lighter fluid that ends up getting the chance to migrate through, and the lighter and more mature fluid gets the chance to migrate through the system. And if we have stacks of systems like this, we kind of get what I call this kind of mushroom effect, where you have a stalk and you have a cap. And what happens then is that as the light fluid continues to come through, it pushes the heavy fluid down dip. And so again, we've got this gravitationally stable system here. And so the head of this mushroom here has a whole range of high mature fluid at the top, low mature fluid at the bottom. And because it's always the light fluid that breaks through at the crest, we can repeat the system again and again and again through the stratigraphy. And this is kind of an example of where, again, we don't want to diagnose false compartments between here and here just because we haven't really thought very carefully about the filling history of the field. So these are some classic mistakes I see. And so compartmentalization to me is not a geochemical problem. Geochemistry is easy. You just measure things in the lab. It's really what it means in terms of reservoir architecture, and then the reservoir architecture in the context of how the reservoir is side filling from the first reservoir and with the potential for overturning, or do we have this kind of mushroom type behavior where we're going to create these stack pays with variable fluid properties that are perfectly continuous, even though they look like they have different fluid types. So a couple of filling here from some of that early work. I think many of you are probably familiar with fluid fingerprints, and you can measure these little peaks, and it's all kind of groovy and everything. I'll show you some examples where you can do this with much more basic data. And so, yeah, this can be useful if you don't have a clear fluid fingerprint, and you can make these star diagrams and dendrograms and all this kind of groovy stuff. But like I say, I really don't think the limitation on understanding reservoir architecture is geochemical. It's really about what do these differences mean, not whether we can measure them or not. And there was a classic example. I'm going to skip through this because this is actually the Chevron produced a really, really nice initial case history of how to use these kind of data and they showed how they remap the fault blocks in a shelf, in a Gulf of Mexico shelf field. These are actually shelf fluvial reservoirs and not deep water reservoirs, but you can go to this resource here and see how they use this. This is probably one of the first examples of GC fingerprinting. Well, what I wanted to come back to again is the physics of reservoir compartmentalization. And this is really what the lab at BP focused on in the late 80s. And here's an example from the Forties field. It's a Paleocene turbidite reservoir. It's draped over. It's a giant reservoir. It's about 2.6 billion barrels of cumulative production here. And originally it was thought to be, I think it was originally a braided stream deposit when it was first discovered in the 70s. The reservoirs were so thick and apparently continuous that the only other analogy that people had seen was braided rivers, and so it was only with further investigation they realized these were deep water turbidite fan sands. And so what William did here was basically looking at a physical property versus depth. We're looking basically this is the GOR, the saturation point of this part of the field. So basically this part of the field has higher GOR, it has lower density, and this part of the field over here to the west has a lower GOR and higher density here. So now here we have a gravitationally unstable situation. We've got fluid here that is deeper or at the same depth as the fluid in the more up dip part of the field. And this was a result of a unitization battle between Shell and BP. Shell owned this part of the field, BP owned this part. Shell were trying to argue for unitization. And what William was able to argue was that actually, although this looks like one field, must be, because of the overturning rate here would be so high, therefore it can't be a mixed reservoir, it has to be some kind of stratigraphic barrier. And at the time, that could not be seen with the seismic of the day. This was back in the 70s and 80s, it was really poor quality seismic. And so he was able to demonstrate that actually this field should not be unitized because effectively over here is a separate reservoir because of this this sort of know, this is a model of the reservoir. Now we know that this is a basin model that was created to try and replicate the reservoir filling in history, and so we know that this higher GOR fluid, and we can relate this to the higher maturity of the kitchen in this part of the versus the charging western field, which is significantly lower. To tie this together with the filling history of the reservoir. This is just an example of a field from the Gulf of Mexico. It's the lobster field. It's on the public data. We've just done a study, a field-wide study for petroleum system study of the field for a client here. But I'm just showing you the published part of this data, and the sort of first clue about so we have a fault block that's coming off of a salt high here. We've got fault seal on both sides of it, but you see that the apparent contact from the seismic is already giving us a clue that this is not just a sheet sand from top to bottom, and we have to have some kind of division in the system. Generally, the turbidites will be coming from north to south during deposition of these turbidites. And again, if I showed you a correlation log of this field, you'd be very tempted just to correlate all of these massive sands together. But clearly, even from the seismic, we see there's something very different. And what we're able to do here, even with this old saturate GC stuff here, you can see that there are different fingerprints within these different wells here. So wells 10 and 2 on the right-hand side of the field, and wells 7, 4, and 5. And so really the final interpretation of this, where we look at the fingerprints, what we find is that really this is a series of offlapping lobes that, if you're not careful, you would just correlate them all along here. But we see with the different fluid fingerprints in here that are actually caused by differential amounts of biodegradation in this case. So again, we want to be careful that we don't do the up dip down dip thing. Here it's really the lateral changes across the strike of the orthogonal to the depositional system that's been revealed by these fluid fingerprints. And this is a case where we would expect it is actually a graded column, and we do see a difference in density from the top to the bottom. But this is a lateral change that we're seeing from lobe to lobe, and it's really the sort of offlapping nature of these lobes here that's really controlling the production of the field. And so, one of the drawbacks with using producing data for fingerprinting as well is that often it's not clear. Often, with MDT data, it's clear where the sample came from. Here, we actually have a little bit of ambiguity as to where the sample came from because of it was completed against multiple zones. So I just wanted to show you these examples. These are both deep water turbidite systems. In fact, lobster has the highest reserves density of any field in the deep water Gulf of Mexico. The reservoir is about 4 million years old. And so again, up and down column, we have a stratified column, so we don't expect to be calling out fingerprint differences from top to bottom because of the grading. So that would explain those differences. And it's really the lateral variations here that we're able to diagnose with the fingerprints. So I think that's really just the kind of that's in 20 minutes. That's really just the whole subject of reservoir geochemistry, all in that. But hopefully I've impressed upon you the need to think about the filling history, and you don't want to just basically interpret every fluid fingerprint as a compartment. And in fact, I think geochemists have created a lot of mischief, unfortunately, by doing things like that, absent an understanding of the filling history and the architecture of the reservoir. So again, another call for integration, an integrated answer, and a holistic petroleum system analysis of the field should always predate the attempt to do a fingerprinting study in our view. Okay, so I think that's really where I'm going to leave it. Susan, do you want to open it back up to discussion?
Sorry, Beth.
Are you there?
Yeah, I'm here. Mute issues.
Okay.
Yeah. So anyway, I think this is a really great time to address some of the questions that have been coming in. So the first one is a quick question. Do the 4 types of splays, frontal, crevasse, et cetera, mentioned, have the same stacking pattern?
That's a good question. I think how most companies approach that is there's a number of different outcrop analogs around the world that expose 4 or 5 different types of splays. You've got the Taranaki Basin, New Zealand. You've got Northern and Southern California, Sacramento Basin, the Coast Ranges along California, the Jack Fork, Ainsa Basin in Spain, Tabernas Sorbus, the Ross Sandstone, Ireland. And so how to gather those data is to identify them and then measure the stratigraphy through them to find out what are the key differences.
That's interesting.
Yeah, so that's how those data sets are gathered, and they're different from system to system. So what you'd find may look like a overbank splay in one system, maybe a crevasse splay in the other, just because you're dealing with different grain sizes, different sizes of flows, and the level to which, for example, for the crevasse splays, level to which it eroded down the levee and brought sediment into the overbank. But, you know, that being said, the channelized splays should be some of the smallest because they're filled by underfit flows. So we can start to predict what they would look like. For the overbank splays, they should be finer grained, less long-lived, thinner stratigraphic intervals than the bigger brother of the crevasse splays, which should show more signs of erosion, maybe even some hybrid event beds if they're ripping up mud from the levees. And then the frontal splay deposits should be the most refined grain size fraction because the flows made it all the way to the end of the system. Now, those are some basic rules of thumb. Your basin will probably differ a little bit, but that's a good start.
Well, that's great. So here's another question. What if the pressure data is from the same compactment prior to faulting?
What if the pressure data is from the same compartment?
Well, I guess it must be compartment. It says compactment, but I think he means compartment prior to faulting.
What if the pressure data is?
Yeah, I just am reading the question. So Adelanke and Bola, if you are here, if you'd like to clarify.
I'm not quite sure what the question is. If we could get a little bit more detail on that. Yeah. So generally, I would say that the pressure data is a signal that comes from the cumulative fluid flow up to the present day. So I think it's hard to have a pressure at some point in the past that hasn't been modified after the subsequent event, right? So the pressure is continuously evolving until we measure it the present day. So I'm not sure if I understand that. I don't think you preserve pressures and then preserve them after you fault a reservoir. The pressure is going to continue to evolve in those 2 separate compartments. But I'm not sure if I understand the question.
Yeah, I know that it is a little bit challenging. Okay, so here's a question for Dr. Andy. I would like to know what can be defined as a threshold in compartmentalization. In the case of tight reservoirs, how low does the mobility, porosity, and or permeability have to be defined, such as similarly for carbonate formations? Okay, this in the chat. You might take a look at it. I'm not sure that reading it made it very clear.
Is it it's coming back to the filling history diagram, maybe? So maybe we can put that up again. So really here I was showing some examples of where there just isn't enough, just simply isn't enough geologic time in the whole history of the Earth, basically, to overturn. So here we're dealing with 100 nanodarcies is a typical system, and this is a gas viscosity. So the combined, the K over mu on that one is incredibly low. The Basin would be probably like 5,000 nanodarcies. So that has not overturned. So that would be, yeah. So the back, but it's just fluid. So the Basin would probably be a similar similar thing like this. So I think we're down at 1,000 nanodarcies. Thousands of nanodarcies kind of permeability is where we would, it's got to be somewhere in the thousands, maybe 10,000 nanodarcies, something like that. And it depends whether it's gas or oil as to whether, because it's the mobility, not just the permeability. So I don't have an exact number, but it's probably somewhere out there in the tens of thousands of nanodarcies. Or like, a fraction of a microdarcy is where you start to, go from something that's, and again, it depends on the time, right? So the filling history. So the filling history of the Basin and in the Permian Basin, our burial histories that we use have that system was filled 35 million years ago before uplift and erosion. So they've had 35 million years to try to overturn there, and they haven't overturned. And so there are probably some key examples around the onshore US where you could try to figure out what that kind of boundary is between overturning versus not overturning. But I must admit, I haven't seen an unconventional reservoir. I mean, the Basin's probably the most permeable I've ever seen. And that one still hasn't overturned. So it's somewhere much higher than the examples that we have in the onshore US.
Good. So we have time for one more. And so this looks like it's for Jon. For a thin bedded reservoir, how can one tell if it is a levee system or a distal lobe system?
Oh boy, wow, this person's been doing some studying. That's a really tough question, really good one. One place you might want to start is looking at grain size distributions, because some of the models proposed by Kane, Hodgson, others who studied a lot of levee successions said levees should be overall finer grained than what you get from the distal lobe setting. But again, this is going to be really detailed work. Some of the bed types, you may expect more HEB or transitional flow deposits if you're in the distal axial portion of those frontal splay complexes versus stuff you would get in the levees. You may get more turbidites because they're off axis, but there's been exceedingly few studies that have proven this. So again, that's why your question's so good. Stacking might be a wash. I don't know anyone who's done a really good analysis between stacking patterns between those. So that may leave you with looking at the paleocurrents. Paleocurrent should show subtle divergence from the main flow in the channel, which should represent what the frontal splay complex looks like, even in the distal margin, versus the levee, which should be going a little bit at an angle to that paleo channel flow. So that's one way to start, but we could probably brainstorm more examples with time.
That's interesting. So I noticed that a lot of people have been entering the meeting, like about 10 people just in the last couple of minutes, which makes me realize that not all parts of the world changed, all countries changed the same weekend. And so I think that some parts changed and now, so that's why they're entering now, but I just want to let everybody know we recorded it. So if you've registered, you'll get a link to the recording.
Susan, if I don't have to rush away, so if people have more questions, I'm happy to stay longer. I don't know about you, Jon.
Well, let's do 5 more minutes, and then we'll. Okay, so it looks like Andy, in the case of turnover rates of reservoirs, wouldn't capillary pressures and bore throat size control or hinder that overturn?
It's not a capillary pressure problem because it's basically I'm talking about a continuous. We're talking about the permeability and mobility inside the reservoir body here, right? So we're capillary pressure differences in grain size and so on are going to determine the saturation and where the oil is, but it's not this is a viscous problem. It's not a capillary or saturation problem. It's basically to do with the rate at which fluid can move. So it's not really a capillary pressure, although capillary pressure and permeability are obviously linked through pore throat size. So it's the kind of grain size. So the grain size and the permeability and the pore throat size is going into the number that we use here in terms of the permeability, right? So, and then the fluid viscosity is playing the other role. It's a K over mu problem because it's a fluid flow problem. It's not a saturation capillary problem. That makes sense, hopefully.
Does to me.
It does. I'll just go off mute if you can hear me. But yeah, that makes sense. And I appreciate the answer on that and appreciate it. Thank you.
Pleasure. Okay.
So can post-production effects be responsible for those filling migration of light HC?
Post-production. Oh, you mean like if you drop it below bubble point?
I'm just reading the question.
Is that
like if you're here, you can clarify.
Does that person want to unmute and try to?
Yeah, good idea.
Would you like to
Okay,
rephrase
hi,
the question?
Andy. And yes, this is Adilan Kebola that asked that question. So, I was going through your, excellent discourse on the filling from the deeper reservoir to the lower reservoirs. So over the years, if you have been producing, for instance, from these complex reservoirs and you have exactly close to like 50 wells, the understanding is that the intra-reservoir shells that were competent some years back and the post-production effect, migration of the fines and all of that. I'm asking that, would that be part of these filling styles, leak phenomenon that you discussed here? That's my question.
Well, yeah, I mean, once fluids start charging around, if the reservoir goes below bubble point or whatever, then really, that's not something. I'm just trying to understand how the reservoir is set up before we do all of our crazy stuff with, moving fluids around within it. So I don't know. I don't really have a comment on trying to do this on an old field. I think it would be extremely challenging. But I think the thing on an old field would be to try to go back to pre-production materials or like core or something like that, to try to get back to the rock record and see whether, but by going back to the initialization of the field before it was produced, whether that provides some insight into what happened during production. If that's I'm not quite sure how to answer your question. It's going to be really complicated to try to understand it after production. And in fact, in that lobster study, we only used the wells up to the first, to construct the graded columns and the initial initialization of each of those reservoirs, which all have these very subtle. When you look at carefully, these very subtle pressure effects on them, although they're all individually graded from top to bottom, because the mushroom we put the in that case is up here. Basically, the crest at every level is up here, and so it's like a half mushroom here, where basically you've got leakage from one lobe, and in fact the leakage is sort of, you can see here these lobes are sort of partially overlapping, and in fact it turned out that the pressure data is always really instructive. So it turns out that the fluids coming in from this level, if you look at this highest overpressure reservoir, and it's actually leaking down through the bottom seal. We've seen that in several fields now, where we're actually, sounds crazy in the Gulf of Mexico, but you're actually leaking downward through the bottom seal. And this column here is about 4,000 feet, so you've got a good head of fluid on there. And actually, you charge down first, and then once you charge down, then basically you start to charge upward into these lobes, but the fluids coming in, it's very difficult because here we're in a well basin. It's really difficult to figure out where the parent chimney is coming into the field. But once it gets into the field, then it's the top of the column here, it's leaking down through the bottom seal into these guys, and then eventually it's leaking sort of laterally and upward into these shallower lobes. Well,
that's interesting. Thank you for the in-depth response. I know we could keep on going for a long time, but we're out of our time commitment. And so unfortunately we have to say, come back to the next events. And also I will be sharing the chat questions with Jon and Andy, so they may wish to contact you, or you can email them. So thank you to both of you. Really appreciate this wonderful webinar. So thank you.
Yeah, thanks to everybody for participating. Hope it was useful.
Excellent.
Thank you very much.
So it looks like we've got some.
Thank you very much, Susan. Thank you, Andy. Thank you, everyone.
Pleasure.
Thank you. So really appreciate it. And
are we staying on, Susan, or do we need to stay on for anything as a wrap up, or are we good?
We're good. I'm just stopping recording.